Introduction. Hey kids, today we learn ray optics and optical instruments. You must hear that in desert one must have a misleading appearance of water at a certain distance. So now the question arises that why it happens. The answer is that the illusion of water is due to total internal reflection. It is optical phenomenon that creates illusion of water with inverted images of distant objects. So, throughout this module we learn reflection and refraction of light. Objectives. At the end of this lesson, you will be able to explain reflection of light by spherical mirrors, state laws of refraction, understand apparent depth, explain total internal reflection, discuss applications of total internal reflection. Reflection of light by spherical mirrors. Reflection. The angle between the incident ray and the normal to the reflecting surface is called the angle of incidence. The angle between the reflected ray and the normal to the reflecting surface is called the angle of reflection. Laws of reflection. The angle of incidence is equal to the angle of reflection. The incident ray, the reflected ray, and the normal to the surface lie in the same plane. These laws hold at each point on any reflecting surface, whether plane or curved. Spherical mirrors. A mirror formed from part of a spherical surface is called a spherical mirror. There are two types of spherical mirrors: concave mirror, convex mirror. The spherical mirror, in which light is reflected from its inner concave surface, is called a concave mirror. The spherical mirror in which the light is reflected from its outer convex surface is called a convex mirror. The spherical mirror has a radius of curvature r, and its center of curvature is located at point C. The geometric center P of a spherical mirror is called the pole. The line joining the pole and the center of curvature of a spherical mirror is called the principal axis. Sign convention. The distances measured in the direction of incident ray are taken to be positive, and those measured opposite are taken to be negative. The heights measured upwards are taken to be positive, and those measured downwards are taken to be negative. Focal length of spherical mirrors. Rays that travel close to the principal axis of a spherical mirror and make small angles with it are called para-axial rays. The point F is called the principal focus of the mirror. The distance FP between the pole and the focus is called the focal length of the spherical mirror, denoted by F. Relationship between focal length and radius of curvature. F is equal to R by 2. Images formed by a concave mirror. When the object is beyond C, the images A. between C and F, B. real and inverted, C. smaller than the object. When the object is at C, the images A. at C, B. real and inverted, C. same in height as the object. Images formed by a concave mirror. When the object is between F and C, the images beyond C, real and inverted, larger than the object. When the object is between F and P, the images behind the mirror, virtual and erect, larger than the object. The mirror equation. The given figure shows an object AB and its image A', B' formed by a concave mirror of focal length F. For paraxial rays, MP can be taken as a straight line perpendicular to CP. Then the two right-angled triangles A', B', F and MPF are similar, so that A dash B dash by MP is equal to B dash F by FP is equal to B dash P minus FP by FP. Since MP is equal to AP, we can write A dash B dash by AB is equal to B dash P minus FP by FP. Name it as 1. Since angle APB is equal to angle A dash PB dash, the right angle triangles ABP and A dash B dash P are also similar, so that A dash B dash by AB is equal to B dash P by BP. Name it as 2. Comparing equations 1 and 2, we obtain B dash P minus FP by FP is equal to B dash P by BP. Name it as 3. On applying the sign convention, we get object distance BP is equal to minus U. Image distance B dash P is equal to minus V. Focal length FP is equal to minus F. So, equation 3 can be reduced to minus V minus of minus F by minus F is equal to minus V by minus U, or 1 by V plus 1 by U is equal to 1 by F. This relation is known as the mirror equation. Linear magnification, M. The ratio of the height of the image, H dash, to the height of the object, H, M is equal to H dash by H. For the given figure, linear magnification is minus V by U. Example. An object is placed in front of a concave mirror of focal length 10 centimeters. What should be the position of the object so that its image is at a distance 20 centimeters in front of the mirror? Solution. Given f is equal to minus 10 centimeters, v is equal to minus 20 centimeters. 1 by v plus 1 by u is equal to 1 by f. 1 by u is equal to 1 by f minus 1 by v. 1 by u is equal to 1 by minus 10 minus 1 by minus 20. It implies 1 by u is equal to minus 1 by 10 plus 1 by 20. 1 by u is equal to minus 2 plus 1 by 20. U is equal to minus 20 centimeters. That is, object should be at a distance 20 centimeters in front of the mirror. Refraction. When a beam of light encounters another transparent medium, a part of light gets reflected back into the first medium, while the rest enters the other. The phenomenon of the change in direction of a beam of light in one medium when it enters a second medium obliquely is called refraction. The angle r between the refracted ray and the normal to the refracting surface is called the angle of refraction. Laws of refraction. Laws of refraction. The incident ray, the refracted ray and the normal to the surface lie in the same plane. The ratio of the sine of the angle of incidence I and the sine of the angle of refraction R is constant for a given pair of media. This rule is called Snell's law. Mathematically, Snell's law gives sine I by sine R is equal to n21, where n21 is a constant called the refractive index of medium 2 with respect to medium 1. If n21 is greater than 1, the refracted ray bends towards the normal. If n21 is less than 1, the refracted ray bends away from the normal. Higher the refractive index of a medium, the more it is optically denser. Apparent depth. Due to refraction, the object in another medium, say in water, appears to be raised. Total internal reflection. When a ray of light is incident on the boundary from denser to rarer medium, it is deviated away from the normal. With increase in an angle of incidence, the angle of refraction increases. For a certain angle of incidence in denser medium, the corresponding angle of refraction in rarer medium is 90 degrees. This particular angle of incidence, for which the corresponding angle of refraction is 90 degrees, is called the critical angle, denoted by C. If angle of incidence is increased beyond the critical angle, the incident ray is not refracted but returns in denser medium following the laws of reflection. This phenomenon is called the total internal reflection. Conditions for total internal reflection. The ray must pass from denser medium to rarer medium. The angle of incidence in the denser medium must be greater than the critical angle for the given pair of media. Relation between refractive indices of media and critical angle. If ND and N are the refractive indices of denser and rarer medium respectively, then from Snell's law, sin I by sin R is equal to NR upon ND. For critical angle incidence, I is equal to C and R is equal to 90 degrees. Therefore, sin C by sin 90 degrees is equal to NR by ND. It implies sin C is equal to NR by ND. If VR is speed of light in rarer medium and VD that in denser medium, then sin C is equal to VD by VR. Total internal reflection in nature and its technological applications. Mirage. In deserts, sometimes a man sees an inverted image of a tree, which gives a false impression of a pond of water near the tree. This is called mirage. Sparkling of diamond. The critical angle for diamond-air interface is very small, nearly 24.4 degrees. When light from an external source enters in a well-cut diamond, it suffers multiple total internal reflections inside the diamond. When at any surface, the angle of incidence is less than 24.4 degrees, only then it may refract out. Thus, the light entering the diamond from all directions emerges out from some directions. Therefore, looking from these directions, the diamond appears sparkling. Prism. When a ray is incident normally on any refracting surface of prism, it passes undeflected and becomes incident on glass-air interface at angle 45 degree, which is greater than the critical angle 42 degree, and so suffers total internal reflection. A total reflecting prism may be used to deviate the rays through 90 degree, to deviate the rays through 180 degree, and to erect the inverted image without any deviation. Optical fiber. An optical fiber is a device based on total internal reflection by which a light signal may be transmitted from one place to another with a negligible loss of energy. Did you know? From 1670 to 1672, Newton lectured on optics. During this period, he investigated the refraction of light and reflection of light. Willebrord Snell gave his theory on refraction of light in 1621. Summary. Let us summarize what we have learned. A mirror formed from part of a spherical surface called a spherical mirror. The mirror equation: 1 by V plus 1 by U is equal to 1 by F. The phenomenon of the change in direction of a beam of light in one medium when it enters a second medium obliquely is called refraction. Snell's law gives sin I by sin R is equal to N21, where N21 is a constant called the refractive index of medium 2 with respect to medium 1. Conditions for total internal reflection: the ray must pass from a denser medium to a rarer medium. The angle of incidence in the denser medium must be greater than the critical angle for a given pair of media.